Next topic in assignment problem is an assignment problem with maximization case. How to solve an assignment problem with maximization case? We have a technique, Hungarian technique, to find an assignment which minimizes the total cost of assignment. So to use same technique for a problem with maximization case, we have to convert the maximization problem into minimization problem and use the same method, Hungarian method. What is the procedure for this conversion? Select the greatest element of the given cost matrix. We have to select greatest element and subtract each element of the cost matrix from this greatest element to get modified matrix. On this modified matrix, usual algorithm of minimization problem is applied to get optimal solution. Now let C suffix RK denote greatest element of the cost matrix. CRK, C suffix RK. Now from this element we subtract the element Cij of the cost matrix, and suppose that this difference we denote by C dash ij. C dash ij is a general element in the modified matrix and it is obtained by subtracting Cij from CRK. CRK is the greatest element. It is a constant number, it is a constant and it is a greatest element of the cost matrix. So whatever element we get, we denote it by C dash ij. So this is a element in the modified matrix, and let Z dash denote this sum C dash ij into xij. So this is a mathematical formulation we have seen. We have seen in the mathematical formulation that using Hungarian method we minimize this cost. Right. This is a cost. This is a cost of which assignment? This assignment is an assignment obtained from the modified matrix. If this is not, these elements are not the elements of original cost matrix. These numbers C dash ij are obtained by subtracting Cij from CRK, where CRK is the greatest element. So this is the objective function. It is called objective function. This is the objective function and it gives you the cost of assignments for this modified matrix. This gives you total cost of assignment. in modified matrix, revise matrix. Now let us substitute the value of C dash ij. C dash ij is this difference. We have subtracted Cij from Crk to get this C dash ij. Into Xij as it is. So let us separate this Crk into Xij minus Cij into Xij. This is a summation over first term minus summation over second term. We can separate this sum. Now we minimize the objective function z dash. This is the objective function for the modified matrix. So minimize it using the Hungarian method. Now what is the effect of this minimization, minimizing this objective function for the modified matrix? Let us see on the right hand side. It is minimization of this right hand side. Now look at the product Crk into Xij. Crk into Xij. Xij takes two values, 1 or 0. Xij is 1 where we made an assignment. Otherwise, if we do not made an assignment in a cell, in that case Xij is 0. So this product is either Crk or it is 0. Right. So this, and now how many Xij are non-zero or how many Xij takes value 1? In the solution, it is equal to the order of the matrix. In solution, n values of Xij are non-zero. That means we made how many assignments? We make how many assignments in the, when we solve the assignment problem? We made n assignment. N means order of the matrix. If it is, the order is 5, we in the solution we get 5 assignment. That means 5 values of Xij are 1. So how many Xij are 1? Equal to order of the matrix n. Right? And this product is Crk in that case. So how many Crk elements are there? Equal to n. For n values of Xij, we get 1 here. So this is a sum of Crk plus Crk plus Crk n times. So it is a constant. This number is a constant. Plus minimum value of the second term. Second term is minus double summation Cij Xij. Now minimum of negative, minimum of minus f of x. Suppose there is some function. So if you want to take this negative sign outside, the minimum, we have to change this minimum value to maximum. So it is equal to minus times maximum of f of x. So if this is some value with negative sign and we want its minimum value, and if you take this negative sign common, then it will be equal to minus times maximum value of whatever is the expression. So minimum of negative term is equal to negative of maximum of this term without negative sign. So minimum of this expression changes to maximum of this expression if you take minus 1 common. So on the left hand side we get minimum value of z applying the same technique, Hungarian technique. But what is the effect on original objective function? When we apply Hungarian method on the modified matrix, at the same time, we maximize the same assignments will maximize the original objective function, right? So here we apply Hungarian methods on the revised matrix. So that will give you maximum value of the original objective function. So the procedure is this: we have to subtract all entries from the greatest entry in the cost matrix and we get revised matrix. On that revised matrix, we apply Hungarian method to get minimum value of the new objective function z dash. But when we obtain minimum value of z dash, in that case we get maximum value of z. That is, z is the original objective function. That is, this is the objective function for the original matrix, and this is the objective function for the revised matrix. So we apply Hungarian method on the revised matrix or modified matrix, and you will get maximum value of the original objective function. All right, let us solve one example on maximization case. So the problem is solve following assignment problem for maximum profit of the objective function is maximize the profit, that is, find out the assignment which will give you maximum value of z. Z is objective function, double summation Cij Xij in the mathematical formulation. So this is an assignment problem with maximization case. This is an assignment problem with maximization case. So we first convert it to a problem with minimization case. And what is the procedure for this? Select the greatest element of the cost matrix. Here, the greatest element in cost matrix is, look at the first row, 16, 10, 14, 11, second row, 14, 11, 15, 15, third row, 15, 15, 13, 12, fourth row, 13, 12, 14, 15. What is the maximum number in the cost matrix or maximum cost in the cost matrix is 16. So here the greatest element in the cost matrix is 16. So what we will do, subtract all the entries from 16 to get modified matrix on which we apply usual algorithm or usual method. So to get modified matrix or revised matrix, subtract all the entries in the cost matrix, from this greatest element, from 16, we get following modified matrix. Modified or revised matrix, on which we apply usual algorithm. So let us subtract all the entries of the given cost matrix from 16. We get 16 minus 16. In the first cell we get 0. Then 16 minus 10. Here is the entry 10. Subtract 10 from 16. We get 6. Then subtract 14 from 16. We get 2. Subtract 11 from 16. We get 5. Subtract 14 from 16. We get 2. Subtract 11 from 16. We get 5. Subtract 15 from 16. We get 1. Then in the second row, in the third row, subtract 15 from 16. We get 1. 1. Then subtract 13 from 16. We get 3. Subtract 12 from 16. We get 4. Subtract 13 from 16. We get 3. Then subtract 12 from 16. We get 4. Subtract 14 from 16. We get 2. And subtract 15. We get 1. Now this is a modified matrix or revised matrix. On which we apply usual algorithm, that is Hungarian method. Now we apply Hungarian method on this revised matrix. So what is step 1? Subtract smallest element of each row from all the entries in that row. So let us apply Hungarian method. First step is subtract minimum element of each row from all the entries in that row. So in the first row, what is the minimum or smallest element is 0. Subtracting 0 will not change the elements in the first row. So the elements in the first row are 0, 6, 2, 5. Now second row, smallest entry is 1. So subtracting 1 from all the numbers, we get 2 minus 1, 1, 5 minus 1, 4, 1 minus 1, 0, 1 minus 1, 0. In the third row, what is the smallest number? It is 1. So subtract 1. So 1 minus 1, 0, 1 minus 1, 0, 3 minus 1, 2, 4 minus 1, 3. Then Row number 4, smallest entry is 1. Subtracting 1, 3 minus 1 we get 2, 4 minus 1 we get 3, 2 minus 1 we get 1, and 1 minus 1 we get 0. So this is a matrix obtained by performing step 1 of Hungarian method. Now apply step 2. What is step 2? Repeat step 1 for columns. That is, we have to select smallest entry in this row. What is the smallest entry in this row? 0. And when we subtract 0, it will not change. Similarly, in the second row, what is the smallest element? Is 0. When we subtract 0, the elements will not change. Similarly, in the third row, the smallest number is 0. And if you subtract 0, the numbers will not change. In the fourth row again, smallest number is 0. So when we subtract 0, the numbers will not change. So after application of second step, you will get same matrix. Application of step 2 of Hungarian method will give you same matrix. So step 2. What is step 2? Repeat step 1 for columns. It will not change the matrix. So apply next step. So step 3. Cover all zeros with minimum number of horizontal and vertical lines. Let us apply step number 3. Starting from the first row, we look at the rows containing single zero. So first row contains single zero. So when we made an assignment in a row, we have to draw a vertical line. So draw the vertical line. Now there are two zeros in the second row, and in the third row there is a single zero because one zero is already crossed. So we made an assignment here. In the third row there is a single zero. So we are making an assignment in a row, so we have to draw a vertical line. All right. Now in the fourth row there is a single zero. So use it for an assignment and draw the vertical line. Right. Now after fourth row, you can look at the columns with single zero. There is only one column left. There is a single zero in this column. We can make an assignment using this zero in the third column. And when we made an assignment in a column, we can draw a horizontal line. Or if you look at the row number 2 contains single zero, so we can make an assignment in a row. Similarly, if you look at the third column, then there is a single zero in the third column. We can use it for an assignment, and when we make an assignment in a column, we draw a horizontal line. So either you can draw a horizontal line or you can draw a vertical line. So let us draw a horizontal line, assuming that we are making an assignment in a column, in the third column. So third column, this is an assignment, and we draw a horizontal line. All right. So how many lines we have drawn? Number of lines are 4. Order of the matrix is 4. So this is an optimum assignment. So number of lines. Horizontal and vertical lines are 4. It is equal to order of the matrix. So this is an optimum assignment. It is obtained by Hungarian method. Therefore, This is an optimum assignment. So what is the optimum assignment? Let us write down. The optimum assignment is A is assigned with the first, that is job A is assigned to the first machine, B is assigned with the third, C is assigned with the machine 2, and D is assigned with 4. This is the optimum assignment. A is assigned with 1, B is assigned with 3, C is assigned with 2, and D is assigned with 4. So this is the optimum assignment. Now we write the optimum assignment cost. Now in this problem, this is a problem of maximization case. So you will get maximum assignment cost. Therefore, the maximum assignment cost, that is profit, by Hungarian method is, now we will take the costs from the original matrix. So let us see what are the costs we have to use. We have to use A is assigned with 1. So C11 in the original matrix, C11. So this is C11, 16. Look at the number, 16 is a maximum in the first row. We are getting maximum profit. Now, second assignment is B is assigned with the machine 3. So C23 is the next cost. C23. This is a cost. So this is maximum. We are getting maximum profit with this assignment. Then let us see what is the assignment in the third row. C is assigned with 2. So what is the cost? Third row, second column. C32. C32. Third row, second column. And finally, D is assigned with fourth machine. So the assignment cost is fourth row, fourth column, C44. C44. So this is again the maximum value. So in this way we get maximum profit. So for that we have to convert this problem to a problem with minimization case by subtracting all the entries from the greatest number of this matrix and then apply usual algorithm on that modified matrix. And a optimum solution obtained for the modified matrix will give you maximum cost for the original matrix. So let us add 16, 15, 15, 15. So the total is 61. 15, 15, 15 plus 16. So it is 61. Maximum profit is 61. So in this way we solve the assignment problem with maximization case. First convert it to the minimization case and then apply usual method, that is Hungarian method or Hungarian technique. So when we apply Hungarian technique on the modified matrix, we get an assignment which maximizes the assignment